All right, today we're going to be talking about quantum numbers, and really way I like to think about quantum numbers at this level is that they're telling us information about where to find a specific electron. So that's where this is all going to come out to be at the end. But first, we need to figure out what quantum numbers are, where are they, how do we determine them, what do they all mean at the end of the day. So let's get to it. So there are going to be 4 quantum numbers that we need for every atom that we have here. They are the N, the L, the ML, and the MS. And they each tell us something differently, and they all have different rules to describe them. So the first one we'll talk about is the N, which is referred to as the principal quantum number. What it does for us is it describes the total energy of our electrons, and it describes the distance of the electron from the nucleus. The values that it can take are any integer, 1, 2, 3, 4, and so on, all the way to infinity. So, when we look at these, what we should expect is that the total energy of n equals 1 is going to be less than that of n equals 2. If we look at the distance of an electron, if we find out that an electron is n equal 3, we will find that it is closer to the nucleus than n equal 4. So that's what that first quantum number is going to tell us about total energy and how big our electron space is going to be, its radius from the nucleus. Second quantum number we can think about, L, here is what we refer to as the orbital quantum number, which really describes the 3D distribution of the electrons, again, around the nucleus here. This is one that I think we're the most familiar with, but we just have to remind ourselves, really, this is telling us about the shape, the S, the P, the D, the F. So in other words, our circle, our dumbbell, our flower shapes that we think about for orbitals, but they actually have a number that's assigned to them. So for example, if we're thinking about the s orbital, that's L equals 0. If we're thinking about a d orbital, that's L equals 2. When we are looking at what possible quantum numbers can exist, the state is L must be 0 all the way to n minus 1. So for example, if I tell you you have an n equal 4 quantum number, L can be 0, 1, 2, or 3. Okay? That's how we define which ones are possible. Next is the ML quantum number, which you might say, hey, it must connect to the L quantum number somehow, and certainly it does, and by what is allowable in that state. So let's use our example again of n equal 4, and let's say we have an L equal 2 quantum number that we've just picked at random here. So what allowable values do we have for this magnetic quantum number? Well, ML, in this case, could be equal to plus or minus 2, plus or minus 1, or 0. That's the ones that are allowed here. Now, these are a little bit different in that they are still describing things connected with L, so they're still the same shape, but now they're talking about the orientation. So, for example, if I wanted to think about the p orbitals, I could have a p orbital that's aligned on the z-axis, or maybe it's on the x-axis. So I would have a pz orbital versus a px orbital. This could be positive 1. This could be negative 1. That's all that we're saying with these, is that it's describing the orientation. Which one equals which orientation, that's not going to matter to us, so don't worry about that. Just know that it's telling us the orientation and what the allowable set of quantum numbers is. Final quantum number that we're going to have here is probably the easy one, the ms, which is the spin quantum number, which tells us, quote unquote, the direction of the spin. This is about angular momentum. It has nothing to do with actual rotation. But for an electron, there's only 2 possible choices, either plus a half or minus a half, and it has no dependencies on any of the other ones. So that's nice. Now, when we're thinking about any electron in an atom, every electron has 4 unique quantum numbers that we're going to have to assign to it. So for example, we could look at an electron that could be n equals 4, L equals 2, ML equals 0, and MS equals minus a half. That is for a specific electron. That is one electron in my atom. We're going to have to see how we can actually define those and get those connected here in a minute. So for example, if we were going to look at what we have here, here's an example of having bromine, and let's say we're interested maybe in one of these electrons here in our 3p orbital here. So if we wanted to do this, we'd say, all right, we know we need 4 different quantum numbers, N, L, ML, and MS. From this notation, there's only certain bits of information we could have. For example, we know that n must be equal to 3 because we're dealing with the 3p level. L we could also get because we know we're looking at a p orbital, which is going to tell us that we are in an L equal 1 state because p is 1. The two that we can't necessarily say anything about from this notation is thinking about the ML or the MS quantum numbers. All we could say at this point is L could be what? It could be plus or minus 1, or it could be 0, connecting in back to the L. And for MS, it would be plus or minus a half. That's all we could say at this level. We'll get into a little bit more when we do orbital configurations and orbital diagrams here in another video. And I think that's about all we need to do for this video. So some of these things probably are a little bit rusty in our head, but hopefully you recognize these things. As always, if you have questions about this, let's talk about it in class. Let me know what we need to figure out and how I can help you understand it better. More videos to come because we're going to be building off this stuff and seeing how more of this applies, so be ready for all that. But I guess until next time, be excellent to each other.